Hi everyone, my name is Dimitria Silveria. I am a Carnegie Mellon Scholar from the Robotics International Summer School in 2021. This year, I contributed to the Intelligent Autonomous Manipulation Lab with the research, discovering affordances from visual perception in the Carnegie Mellon Ballbot. The Carnegie Mellon Ballbot is an autonomous mobile manipulator designed to assist humans in tasks such as grasping objects. In order to execute its manipulation tasks efficiently, the robot needs to learn object affordances. Affordances are all the possible interactions that an environment provides to an agent. For example, a button affords the action of pushing. But how can a robot discover affordances? In this research, the Ballbot was provided with behavior primitives in order to explore and learn these affordances through interaction in a simulation environment. This way, the robot will be able to infer from its visual perception which interactions an object affords, preventing it to perform useless actions like trying to switch a button. The simulated robot was composed of a cylinder without the ball in its base and Cartesian arms with 3 prismatic joints, and a sphere playing the actuator's role. A kinetic sensor was placed on the cylinder's top to collect RGB and depth images. The interactions were performed in 3 of the objects shown in the image: the table, the wall, and the cuboid. The collected images were used to obtain point clouds. Then, the robot selected random points in the point cloud to apply the grasp and push actions. Each interaction returned 9 parameters: the forces x, y, and z exerted by each joint, delta, that was the 3D difference between the initial and final object positions obtained from the respective point clouds, and the 3D difference between the initial and final actuator positions provided by VREP. These parameters composed the feature vector to cluster the data using the algorithm X-means, which returned 5 clusters. Clusters number 0 and 2 contained points in the cuboid surface. Cluster number 1 had all the wall points, while cluster number 4 had only table points. The cluster number 3 was composed of points from the cuboid and the table. These clusters, as well as RGB image patches from each point, were used to train a visual classifier. The classifier presented a 82% accuracy over the test set. The algorithm predicted 100% correctly for the clusters number 0, 1, and 4. The low accuracy for cluster number 2 occurred due to the small amount of points for that cluster. The issue regarding cluster number 3 is the presence of images from the cuboid and from the table, which makes it hard for the classifier to recognize a pattern between them. Another problem is the fact that one image could belong to more than one cluster. The cuboid, for example, could belong to clusters number 0, 2, and 3, but the algorithm was able to predict only one class for it. For future work, it is necessary to collect more data, especially using different objects. It is also necessary to train a neural network capable of returning more than one class for each image. Another important step for the future is to use this learning process in the real robot. I would like to thank Carnegie Mellon Robotics Institute and the Intelligent Autonomous Manipulation Lab for providing me with this opportunity. I would also like to thank everyone who somehow worked for this program to happen, especially Rachel Birkin and Dr. John Dola. And last but not least, I would like to thank my advisors, Dr. Oliver Cromer and Soumya Saxena.